Good morning, everybody. I was just told before we commence with this talk that this talk is going to be posted on Google Video. But we're not supposed to ask any confidential questions until the videotaping is over. So if you ask questions, make sure to discreetly obfuscate any confidential information that might be contained within. So it's my great pleasure to announce Nick Weaver. He is a researcher at ICSI in Berkeley, and his research is mostly security related. He told me it ranges from carbon to silicon, and he can tell you what that means.
A good example is one problem I'm working on is user authentication, making it easy enough for my mom to use, but secure enough that I will use, and cheap enough that my bank will pay for, which means that's all the way from user interface to building little dongles. So I'm going to talk about another hardware-based problem, and that's work at building intrusion detection. This is joint work with Vern Paxson and Chema, who's a recent graduate. Also a lot of contributions from others. I'm using a board from Stanford, actual hardware. Stuart, Dan Ellis, funded by a bunch of people whose opinions are my own, not theirs. And it's also how we're thinking about the problem as much as actually building. So this is, in many ways, a work in progress talk. So first of all, I'm going to talk about the intrusion detection system and intrusion prevention problem. So how to detect attacks in the network. The local area network problem. Not only do we want to detect attacks in the network, we need to do it cheaply and at high rate because I want every packet to go through the IDS, even the stuff to the file server. Talk about shunting, which is a hardware mechanism we've built, hardware and software, to allow a lot of IDS traffic to work at high rates, including the hardware, and then how to use it to abuse the network so that you can actually have all your packets go through. But first of all, a correction. I believe that the intrusion detection problem is really how to enforce a policy on the network, not how to detect attacks. Because detecting attacks is hard and gets into this metamorphic arms race. But enforcing policy is a bit higher level, but it also requires more work. So I'll tell in a minute what I mean by that. So the goal of the work is to take a policy-oriented intrusion detection system that's based on first reassemble the TCP streams and then parse the protocols. So for all traffic, try to figure out what the traffic really means. So layer 7 analysis in the buzzword parlance. And then once you understand what it means, then you apply target-specific policies. And so then we want a mechanism that will allow this to run at high rates and inline rather than just being out of band. So our goal is to be able to block attacks as they occur, be able to do this cheaply, be able to process 2 to 4 gigabits on a commodity PC, not a cluster, and also be able to, ideally, do all traffic at a network switch, and using very low-cost hardware and commodity acceleration. And it's based on 2 key things. The key observation is all traffic must pass through the intrusion detection system if you want to block attacks as they occur. But in a heavy-tailed environment, only a small amount really benefits from detailed examination. I'm not going to try to examine all the YouTube video traffic for an embedded exploit, because although there may be an embedded exploit in that massive 50 megabyte blob, the CPU is probably better focused on stopping the lower hanging fruit. And the key technique is, given this assumption, is process 90% of the packets in simple, cheap, imprecise hardware, and 10% or less in software. So before I get in more, it's why should Google care about this talk at all? Everybody knows Google designs their own motherboards. The hardware I'm using is actually relatively cheap. A 4-port Ethernet PHY, a small, not too big FPGA. I'll tell more about those later. and 4 megabytes of SRAM. It's the kind of thing that you could build onto a motherboard for maybe $150, $200 a board. And you might be able to do a more cost-optimized version where it's only a single Ethernet or 2 Ethernets and get the price down to 30 or 40 a board. And basically, this is a design philosophy on the hardware side of do a little compute and memory lookup on the packet and hardware, and then either now know what you can do and do it, and have the hardware do it, and never bother the CPU at all, never bother the memory bus. Or know that the hardware has no clue what to do, shove it at the big CPU, and let God and Intel and Andy Grove sort it out. Because I don't want to build hardware that handles all these obnoxious corner cases. I want to build hardware that only considers the main case. So conventional view of network intrusion detection is distinguish good from bad and either report attacks or block as they occur. In general, we use IDS to refer to both. And in practice, everybody runs them and everybody ignores them. Because you run them because your auditors say you need intrusion detection, and you ignore them because you get all these alerts and false positives and stuff because everybody just runs Snort or the like, and Snort's stateless pretty much. And we spent an hour dragging down a false positive from Snort a little while ago from the Berkeley campus. And in general, you have false positives. A false negative is you miss attacks. These are considered annoying, but not necessarily critical. False positives in an IDS can pollute the log. True positives can pollute the log, too. You don't want to log every failed attempt by all these old worms that are around there because there's just so many of them. A false positive in an intrusion prevention system where you block traffic, that is network autoimmune disease. That is, your security system is attacking your own network. This is really bad. However, we take a different view of the IDS problem. In general, we believe it's policy. You have to learn or define a policy, detect violations, and block as appropriate. And it's not just security. It's usability, efficiency, authorization. These are all policy problems. So this is something we can't do today, but we dream of doing. The corporate policy for BitTorrent. Because on one hand, BitTorrent is evil. It may open up huge liability concerns. On the other hand, BitTorrent is really nice for grabbing those Fedora Core ISOs. So first of all, it gets into fine print, so I'll read them out. Log everything. Who requested what data, when, what peers, duration, volume. Terabyte disk arrays are cheap. When in doubt, just log it, because who knows, you might be interested in that data. Have a local cache. BitTorrent consumes a lot of bandwidth, but it's very easy to make a cache for torrents. BitTorrent, the whole protocol works very well. All you have to do is tell the cache to contact this local user on this tracker, and now the BitTorrent protocol will just shove all the data back and forth between them because they have good links. And at the same time, since it's cached, let's limit the non-cached bandwidth to that host to some reasonable threshold, because we got to pay for every bit that goes across the network. So why should we pay for it? If it's not in the local cache and more than a couple people have fetched it, tell the cache, oh, add this torrent. These are all these peers. Go talk to them. Sort it all out. And throttle the bandwidth because I don't want to pay for it anymore. If our site-wide internet bandwidth is above some threshold, let's just throttle this some more because this is lower priority than the CEO's checking of his Gmail account. If it's possibly a copyright violation, use some heuristics based on file name, who it's talking to, if the torrent's in Pirate Bay. Throttle it heavily, but not completely. This is, make it seem like they're getting really, 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 really crappy performance, and send an email to somebody human to actually take a look. And since these are large files, you throttle them down. It's bad performance. You've got an hour or two to send out the nasty grams. If it's almost certainly a copyright violation, block the connection, report user to security. And these are security problems if you're a company, because this is liability. This is the RIAA comes knocking on your door with a $10 million lawsuit. If the communication itself contains a violation of the protocol, you need a detailed model of the protocol, and you know what the fields are, and you go, this field is out of spec. Probably an attack, report it. And if it contains anything a known attack, block that attack as it occurs and report it. But this is a very hard problem to do, because the first thing I need to do in order to implement that lovely policy is actually understand this god-awful protocol. And so you first need to understand the protocols. And cryptographic protocols are a special problem, but if you're somebody who's suitably evil in charge of corporate IT security, you can get around the crypto protocol by saying, you're telling the IDS the keys or we're cutting off that communication. Companies, the attitude of the company is, you don't have secrets from us, buddy. So if you try to hide something from us, we'll block it. It's very hard to express a good policy. This here was just a pure paper design. If I actually wanted to put it into a form a computer would recognize, we're looking at something that's probably a couple of pages, even once you have all the parsing done. Even simple problems are hard. TCP stream reassembly for a high bandwidth site is this annoying problem that requires hundreds of megabytes of state. And it's adversarial. Attackers can work around it. And overall, this is a really hard problem when dealing with just a little dinky 100 megabit link. But we want to do better, because the problem is how we build our networks. We build a perimeter. So something in the network that acts to check and control data. So point of enforcement, point of control. The problem is a few observations. Once this perimeter is breached, all bets are off. Google's corporate security better hope that I'm not an evil individual, because this little thing could get stuck into some random Google computer and you'd have a problem. So your big perimeters have problems. And part of the issue is something like the firewall NIDS viewpoint. This inside is too big. The bigger, the more scope your perimeter encompasses, the easier it is for an attacker to breach. And once an attacker breaches the perimeter, you can no longer make assertions. The people at the front desk can't make any assertions about where I am, but people who are with me still can. And basically, once an attacker gets through the firewall and gets through the NIDS, they are an insider. So in reality, the bigger the firewall, the more you have to deal with the insider attack problem. The end host, on the other hand, has a real nice fine perimeter. You're protecting only a single asset. So by making your perimeters very fine, you get very good coverage, and in case of a breach, you only lose a little bit. The problem is these systems are pretty fragile. So many of the apps already straddle the system. You escalate to system level privileges, you start running, you blow away the antivirus. And although the virtualization techniques promise to make this barrier here a lot better, your printers are computers, and your printers aren't going to support all that lovely virtualization protection and the like. And let me tell you, if you're a corporate spy, who cares about the computers? If you have a tap in one of these high-end workgroup printers, you basically know everything the corporation does. So the end hosts have weaknesses as well. And thus, we believe what is necessary is policy analysis and enforcement in the local area network. So we believe that what is needed is security at the switch, so that every packet is going through at least some level of analysis. Horribly, this is a dream. This is something we can't do today, but we want to do tomorrow. But of course, this makes the problem horribly, horribly hard. 100 megabit access to the internet, that's about $2,000 a month. You might get down to 1,000. It's a lot of money. A 48-port managed gigabit Ethernet switch with all the bells and whistles, that's $3,000, and I pay it once, and it's maybe $50 a year in power. Also, the local area network is 10 to 100x larger than anything else. Internet for my business, that's 1 to 5 locations. That's easy. Deal with 5 places. Switch, I might have hundreds of switches, even a reasonable institution. And so our goal is to make it as price sensitive as possible. Start with a conventional intrusion detection, try to make it run at line rate using very simple hardware acceleration. And we're starting with 2 pieces, the Bro intrusion detection system, and the mechanism is the NetFPGA-based research platform. So first of all, what is Bro? Bro is a high-level intrusion detection system designed by Vern and Company that's designed to express signatures, specifications, and anomaly detection. And it's centered around analysis and policy interpretation. Packets come in, pass through some filters, go to this event engine, which is parsing the network traffic. The parsers are written in a combination of C and this high-level language called BinPAC. Then the parsing goes up to the policy interpreters, which implement site-specific policy. And so you've got the analyzers, you've got the policy scripts. And you can hook it up to responses. If you scan Lawrence Berkeley National Labs with more than 10 or 20 probes, your IP gets blocked at the border. Just simple little go-away things. So why are we using Bro as a starting point? Well, first of all, it actually does work operationally. The early traffic is often the most important for policy. So for example, connection setup for an SSH connection. You want to see the connection setup. You want to ensure it's not password guessing. And that you can do just looking at the traffic without even having to know what's in it. It's open source. It's extensible. It's also, well, we're at ICSI. We use Bro, not Snort. Institutional bias. And it's policy-focused rather than signature-focused. Because we find that signatures tend to be just too limited. There are too many ways around them. So the other part I'm using is this NetFPGA board developed at Stanford that has a not too big FPGA, something on the order of a couple $100, $100 when you buy it in the boatload crate quantities. 4 gigabit Ethernets coming in, 2 2-megabyte SRAMs, and a PCI bus, a 3332 PCI bus. The network, is vastly more bandwidth than this PCI interface. So basically, you have to process most of the packets on the board, because if you tried to bring too many to the host, it would just drop packets. The internal bandwidth is all 2 gigabit links, which made it relatively easy to meet timing and performance. So why did I use this? It's large enough to be interesting. 4 gigabit Ethernets with control logic and enough space to put in my own code. So enough logic to actually do something real, but small enough to be reasonable. This is not, OK, it's actually 600, but I think it gets below 300 plus when you buy a lot. DigiKey is the most expensive provider for hardware, but they sell you single units, so it's really useful. It's got enough memory to be interesting, 2 megabytes of SRAM. Without reasonable, the memory cost on the board, single unit is 60. Again, it ends up being 30 or less when you buy a large amount. And this is really useful to me, is it's tightly coupled to the host, and it behaves like an Ethernet. If I can't do the decision in hardware, I throw it to the host, and the host sees an Ethernet packet. And there's a Linux driver, ClickWorks, anything that processes packets just sees it as another network device. And there's a revised board in the pipeline that should be about $2,000 a board. So a reasonably cheap board that has programmability and high data rates. So how many know what an FPGA is? OK, then I can largely skip this slide. Basically, cheap to horribly expensive. But as I mentioned, there's this key idea that all traffic must pass through our IDS. Otherwise, we can't do this per policy enforcement. But only a small fraction really benefits by examination. So let's go through another policy example, SSH. Log all connections. As I said, when in doubt, log everything. If it's repeated password guessing, log and block. So block that source for the next day or two. In general, if you're doing an automated block, we find that it's good to just have those blocks release after a little while, because that's good enough to act as a go away, but also good enough that if you have a false positive, it will clear itself up by the time they actually get around to complaining to you. If there's a number of new destinations for that particular source, if it's above a certain threshold, log it. High fan-out's unusual. It should probably be reported. If attacks detected in the connection setup, because you can do something in the connection setup, block that packet before it can actually infect the host. Block that source, log it, and report. When the connection terminates, we want to log a rough approximation of the traffic volume and the time, because this tells you a huge amount of information. Were they stealing 500 megabytes of your corporate secrets, or who knows what, or was it just an interactive session? This tells you a heck of a lot. But in order to do this, all we need to do is examine connection setup. A little sampling of the traffic, like 1 in 1,000, 1 in 10,000 packets, is good enough to get the volume, and connection termination. And so our goal is to provide a simple mechanism that can support this. So what we did is added in an inline element that replaces this whole initial filter network interface model. The shunt's an inline element. It sends the packet up to the event engine, and it's re-injected by the IDS. One of the great things about this event model is how Bro normally processes packets, is it has this event queue. If the event queue is empty, it grabs the next packet. This packet does its analysis. This analysis may trigger more events. Say if it's just a hole, well, the stream reassembler does it, and that's it. And then the next packet that fills in the hole, that might trigger a lot of parsing, which might trigger policy, which triggers all these different events. Fortunately, Bro is not multi-threaded. Bro is single-threaded. So if we just, fortunately, because it allows us to make it in line with a very simple hack. You take the packet, you hold that packet in a thing, you run through the event queue. Once the event queue is empty and it tries to grab the next packet from the interface, you see, was I supposed to drop this packet? If yes, you drop the packet. Otherwise, you just inject it back into the network.
How much latency increase are we talking here?
We don't have a full integrated software path, but just a minimum hardware software path of just sort of a test harness is only in the tens of microseconds. Even if it's up to full software, we expect only a millisecond or two. Because if we can't process packets at that rate, we won't be able to keep up at all. And so the key is this hardware, however, is in front of it is to allow Bro to say, OK, this connection's not interesting me. So basically, for each host or connection, associate an action. Either forward this packet onward. This is an SSH connection. I don't care anymore. This is the big YouTube blob. I don't care for the next 50 megabytes. Forward it for the next 50 megabytes. Drop the packet. Drop the host. This is a bad host. This is a host who's trying to overload my intrusion detection system. Let's just block him completely. Sample the packet with some probability. So I'm monitoring this with a 1 in 10,000 chance. Or, and the default behavior is shunt to the host, and the IDS can easily inject new rules into the system. And each match has a priority, and so you do the highest priority. So you can say, this host is behaving badly. Block him. But all packets going to that host will whitelist those connections at a slightly higher priority, so I can block an offending host from contacting me, but I can still contact him by playing games with the priority. And the IDS controls these tables. And one of the keys is, this is, if there is no match, it goes up to software. So this can be a cache. It doesn't have to be complete. I don't have to track all connections. I only have to track a cache of connections. So Chema extended the API to allow Bro to use shunt. And I've been building this hardware element that's look up the packet in every table. One of the great things is it's very easy for hardware. It's only a couple of fixed lookups because it's a cache. I don't have to do pointer chasing in hardware. You want to make a hardware person scream, have them do arbitrary pointer-based data structures. It's very easy to just go look up in a few fixed locations. And a priority encoder. And then there's a software element to manage the interaction between the two. This is from Chema's thesis on a trace of Lawrence Berkeley Labs access link with his shunt-aware policies. Basically, it allows you to ignore about 80% of the traffic. For SSH, for example, you have to see only a teeny amount of the packet. For HTTP, however, the analyzer had to analyze most of the data. However, we could still reduce the HTTP load by saying forward for sequence, because sequence number gives you an approximation of traffic, and that's just another lookup. It's an additional comparison. Do I need to forward past his sequence or not? And that allows you to bypass another 20% of the traffic. One of the nice things, or not nice things, is that we can't analyze all this CRUD.
So Nick, given that you're giving your talk here at Google, and I would presume that a lot of our traffic is HTTP, do you have any ideas on how to get this even better than maybe even your 20% number there?
I think for Google's point of view, okay, the question is, what about for Google production where you've got almost all HTTP? Could this strategy work? I think it could because you aren't as interested in the outgoing data. You're interested in the incoming data into Google. So you'd probably do full analysis on every request, but the responses are less interesting. You're going to trust that that 50 megabytes of YouTube is truly legit, I'm assuming. So I'm not sure how well this would work for Google, however. However, one other thing, and the reason why I said it is interesting to Google, is not what I did, but how I did it. The notion of you can get real simple hardware offloading some of these problems. If you can turn the problem into, do a couple of lookups, and know that you can solve the problem. One of the problems is about half the traffic at LBL, we don't know how to analyze it all. And this is higher load. One of the things we haven't done is integrate the dynamic protocol detection that Bro now supports into this shunting framework. One of the things that Bro now supports is the ability to analyze traffic as if it's every protocol. So ports are meaningless. Let's analyze everything as if it could be anything and find out what it really is, or if not, give up. So we don't know how that would affect this fraction of traffic.
So what protocols fit in the 50%?
BitTorrent, for example. What protocols fit in the 50%? BitTorrent, for example, we don't have a good BitTorrent analyzer. Skype tends to be a lot of just random traffic. A lot of it's just, here there be gremlins. We don't know what it is. It's just a lot of crud. Of course, there's a couple of huge limitations. Is it offloads the packet transport and preliminary processing, but it actually doesn't reduce the CPU load much. This approach allows you to avoid having to transfer a lot of packets, but Bro's already set up to focus its computation on the interesting stuff. So for all the stuff that doesn't have analyzers on it at all, those things are dropped in the BPF filter. For things like SSH, once the SSH protocol analysis is done, it pretty much just ignores the packets. However, as I said, we want to control all packets in the network, not just ones crossing the local area network. Fortunately, there's this lovely thing called VLANs. VLANs are this beautiful technique to abuse. That what you can do is have every port on the switch be its own unique untagged VLAN. And I believe the SANE project at Stanford is using the same trick as well. So you can only send and receive traffic to that VLAN. Each port can also be tagged on multiple VLANs so that you can send and receive to any allowed VLAN. And you have this added VLAN tag between the source MAC address and the Ethernet length type field. And your Ethernet packets are actually allowed to be slightly larger when you have this tag. Note that the Linux kernel doesn't respect this. Bring in the spec. Sorry, kernel bug that bit me the other day. This gives us the ability to do traffic isolation. That what you do is you have every system on its own virtual area network, and then you have your IDS and ports on trunks for all VLANs. So when a host sends a packet, so in this case, B sends a packet, it ends up going to a rewriting port that either goes, oh, this connection's good. It should be rewritten to this destination MAC and this destination VLAN tag, re-inject the packet, and it goes off to the destination. Or it could be, I don't know what to do with it yet, so you throw it up to the whole IDS. If the IDS, so this allows you to have only a small amount of additional hardware lookup. All you have to do in the hardware is support the notion of, for this connection, rewrite it to this MAC in this VLAN. And that's all you need to be able to do this. So how did we build this in hardware? Is we built simple hardware with software deceleration. What I mean is the software world, you guys love the illusion of infinite state, branches, and infinite processing. The hardware world wants none of that. We want fixed processing. So we do this, this, this. We want fixed state, both in terms of volume, that this is a 2 megabyte SRAM and nothing shall change, and fixed access patterns. So I get a packet, I'm going to need to do 4 memory accesses at these locations. And branches are evil from the hardware viewpoint. Straight line, that's easy. That's just sequential, blah, 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 blah. Conditional logic, you want to avoid. So the idea is to build the hardware simple but faulty. So the hardware uses fixed memory tables and static computation with single-sided errors. So if the hardware can make a decision, it knows what to do. The decision could be let software sort it out. Or if the hardware doesn't make a decision or makes a mistake, the mistake is always let software sort it out when the hardware could have solved the problem. So the API for the shunt is you have infinite capacity, but for the hardware, it's fixed capacity. So for tracking IP addresses, we allow only 2 to the 16 total IP addresses. We can only track 64K IP addresses. And there's a couple of cool cache tricks that I have a paper on that allow you to make this bet more efficient. For tracking connections, we can only track 64K simultaneous connections. Anything else? Let software sort it out. However, this is good enough to get a miss rate that's really low in practice. For sequence skipping, we have 2 to the 15 entries. So for this connection, you only want it valid for the sequence range. You have a pointer, and you say, OK, this destination should be rewritten so that we can support the rewriting. We can support the sequence skipping. And if there's no entry, toss it up to software. However, the software basically has to redo the hardware calculation because this is an imprecise cache, and the software view is you provide the illusion of a infinite capacity API. So I built this by taking this initial design that the NetFPGA group did, which was a 4-port Ethernet, and modified it so in front of every Ethernet, I added some logic where it would read the packet into the buffer. This would read in at 2 gigabits, extract the headers, do some decision. I gave myself a crossbar to memory so that all 4 of these could access the same memory, which the host could access as well. So this is where I do the cache, and the host can get to it. And then decide where to write the packet, and either write the packet to the host, because I don't know what to do with it. Looks like a host packet. Or write to any of the Ethernets. And the Ethernets now effectively have a crossbar. So I have a 5 to 4 crossbar for output, so I can route packets to any destination. One of the cool things, I have to read the packet into the buffer completely because I have to modify it. But once I start writing out the packet to another Ethernet, I can start reading in the next packet because all the memories are nicely dual ported. So this was designed as a nice general building block. It works. It's available as part of the NetFPGA distribution, and I will be updating it for their new board that's coming out. So the hardware works. Developed a couple of cute cache tricks. The hardware works. It'll rewrite MAC addresses. It'll skip sequences. And I have a nice little click API. For stuff that's staying only in the hardware path, 5 microseconds latency. It's, from a hardware viewpoint, I see 5 microseconds and I go, God, that's forever. That's evil. That's vile. When I show that to Vern, he goes, what's a microsecond? There's this mismatch that we really were able to take advantage of. So in terms of future work on this, there's always more bugs to fix. So there's a bug that causes my inputs to freeze up at 450 megabits. That's fixed in NetFPGA 2.1. And we want to deploy it. We're planning on deploying on a mirror of Berkeley's network. So we'll be running real traffic through real hardware. I want to do some other tricks with the hardware, build scan detection. We're working on a cluster bro where we're splitting bro into a cluster. And so you can use this as a load balancer. Our current load balancer is software, but as Berkeley's net continues to improve, we're going to have to make a 10 gigabit load balancer, so we're going to have to look at hardware for that. One of the interesting tricks is you can do this as a router forwarding plane, because what costs money on a router? It's the bloody crossbar. The crossbars are these horribly expensive things, but I can go out and buy a cheap crossbar. It's called an Ethernet switch. So have an Ethernet switch. You have half the ports be external, half the ports going to these FPGA rewriting engines. Packet comes from the Ethernet, goes to a specific port. You rewrite the MAC address, you rewrite the VLAN tag, you decrement the TTL, re-inject the packet, and the Ethernet puts it onto the destination. So there's a lot of other cool tricks you can do with this hardware that we're just only starting to explore. So it's the notion of tricks like this is why Google might be interested. This intrusion detection stuff, you guys just clusterize everything. Just have every cluster node running its own IDS. Who cares? But this style of stuff might be useful, that you might have a role in your data center for shove the packet back onto the Ethernet to someplace else. Why bother the CPU with this? So let's see, conclusions. So although it's still work in progress, we've got pretty good proof that you can take a cheap, simple, cheerful hardware architecture. If you build this as part of an Ethernet ASIC, the additional cost would be a trivial amount of gates in an SRAM. And plus the conventional intrusion detection allows you this high-performance intrusion prevention. Do things by table lookup in hardware. It works well. Make it a cache and let software sort it out. That works really well. However, we're at a limit. We're focused on CPU. We will peg out the CPU once we turn on all these analyzers and dynamic protocol detection, even if we are skipping 80% of the traffic. Skipping 80% of the traffic is still useful because it saves that memory bus bandwidth for something more valuable. But we're still starting to really struggle with limits on CPU time. So we're looking at how we parallelize this problem. We have some ideas, but nothing concrete yet. And so significant research is what else can we do in the local area network? And also, are there other interesting hardware hacks that you can do with this methodology? Do a little lookup, decide what to do, or throw it at the software. The reason why we haven't seen a lot of this in the past is most FPGA boards don't have this good network and good host connectivity. These FPGAs will have embedded processors, but they're only 300 megahertz power PCs, not 3 gigahertz Intels. And I really need that 3 gigahertz Intel to be able to run everything else. So open questions. So questions, comments, flames?
Here, use the microphone, Andre.
I wonder, how do you avoid attacks in which, say, users would send spoofed packets in order to prevent some other parties from communication with the interior?
In terms of the Joe Job style attack, there's nothing really you can do about that simply if you're blocking based on scan detection. If you're blocking based on a real interactive attack, you can't spoof packets and get TCP to work.
Yeah, right. But maybe UDP or some other connection that's present.
In that case, that's a policy problem. It's how do you deal with that? One of the fortunate things you can do is you can start whitelisting those hosts. And the other thing is you can do asymmetric so that, that I'm blocking that host at the border. I can still contact him from internally by playing these priority games. So I see the SYN going outbound. That TCP SYN says, OK, now I'm going to whitelist that connection. So when that connection comes back, I can see it. So that would be the best way. But in terms of dealing with somebody doing that kind of attack coming in, there's not much really you can do about that. Fortunately, however, a lot of places now block spoof packets. There's an economic motive for ISPs to block spoof packets. So that problem's going away. The other thing that concerns us, and this is actually a bigger issue, is we have the fast pass, slow path setup. Fast pass is process and hardware. Slow path is go to the CPU. How do you take down a router? You kill the slow path with traffic.
Yeah, exactly.
If you aren't able to spoof packets and you're getting stuff into the slow path, that's why we have that IP block. That if you have more than 64K IPs able to attack us, you can just blow us off the net with just a brute force DDoS. You no longer have to worry about brute force DDoSing the IDS. If you only have, say, 10K zombies, if I can identify those 10K zombies, I can block them and protect my slow path. So if you're building this for a router, you're still going to want this IP block functionality to protect your CPU.
How come you don't use something like TCP/AC inputs? So like you can enforce the router path on the actual hardware. So like instead of actually allowing the connection to get through, before you do that, you create a TCP SYN cookie.
And rewrite the,
Rewrite.
that would basically require adding NAT functionality into the hardware. That would work, but I'm not sure if that would be a real benefit, if rewriting sequence numbers in the hardware would be a benefit.
I mean, presumably, if I have 10,000 bots, I can just do real TCP connections to you anyway.
Yeah. And the thing is 10,000 bots, my goal is to identify those 10,000 bots and block them. If you have 100,000 bots, I'm not even going to try because you can just blow me out of the water. So it's also only bother enough security to the point where they're going to do something else. My deadbolt on my door lock is not very good. My girlfriend can kick it in. We've proven this in practice when it froze up due to corrosion, but it's still stronger than the window.